We are told that the steam reforming of methane is a viable source of hydrogen. We are given the equation that describes this process, and we want to find the heat of reaction. So to do so, we can use the following information, and these are another series of equations with their heat of reactions given, and I will call these 1, 2, and 3, and these are our sub-equations. So to approach this problem, we eventually want to take all of these equations and get to this equation. So we're going to manipulate them in any way possible, whether it's adding them together, subtracting them, multiplying by constants to derive this. And what's great is that we can also in the same way manipulate these heats of reactions to get our final heat of reaction for the equation. And that will become more apparent as I go through the problem. But the reason that we can do that is because enthalpy is a state function. So that means it's pathway independent. If I want to get from point A to point B and find the heat of reaction, I can do that in multiple ways, moving through many different pathways, and I will get the exact same thing. So we can take these sub-equations and use them to find the heat of reaction. So this can be done in many different ways, and you can verify my answer and do it how you see fit. But I'll walk through how my thought process worked for this problem. So the first thing I noticed is that we want methane on the left side. So I looked at this equation and said, okay, we're starting with methane. My sub-equation number 3 has methane on the right side. Well, I want to flip that. So essentially I want to reverse this reaction. And to do that, I'm essentially just multiplying this entire equation by -1 to reverse it. So this is going to look like this. And I will represent this as -3. And when I say 3, 2, 1, I'm just referring to these sub-equations here. So now that we have methane on the correct side, the second thing I noticed is that we need to get rid of our carbon dioxide. So we have carbon dioxide in this equation, but again, looking back at our final equation, we don't have any carbon dioxide, so we need to get rid of it. And usually this is done by recognizing that carbon dioxide is also in another equation, and in this case, it's equation 2. So we're going to use equation 2 to cancel out the carbon dioxide that we have here. So what we're going to do is take this equation we derived above, and we're going to add sub-equation 2. And we can see that our carbon dioxides cancel. We also have a water molecule that cancels, and our final equation is going to look like this. So I'm going to compare this equation with the process I'm interested in. And the third thing I noticed is that we need to get rid of carbon, because this is not in our final equation that we need. So to do that, I can see that equation 1 also has carbon in it. So we need to use that to cancel the carbon and the equation we derived here. So what we're going to end up doing is flipping or reversing equation 1, which is just multiplying by -1. So we can have carbon on the left side, because if we look here, we have carbon on the right side, so we need it to be on the opposite side to cancel it. And then we're going to multiply that equation by 2, because this carbon has a stoichiometric coefficient of 2. So I'm going to take the equation that we came up with above, which is represented by -3 plus 2, and I'll write that out again. And we're going to add -1, the first equation reversed, multiplied by 2, which looks like this. So we can see that our carbons cancel, and when we add these together, we're going to get the following equation. So again, comparing this to our original equation, which is given in our problem statement, we now have exactly the equation that we need. So we're done manipulating the sub-equations, and we can now find the heat of reaction from all of our steps. So to recap, what we did is we took the equation -3 plus 2, and we added -1 times 2. So this can be translated into finding the heat of reaction of the process we're interested in, because this will be the heat of reaction of equation 3 times -1 plus the heat of reaction of equation 2 plus the heat of reaction of equation 1 times -1 times 2. And those values will look like this. And as a final answer, I get that our heat of reaction is 206 kilojoules per mole.